All right, in our last video we ended up with the conclusion that the torsional spring constant for that one spring that's going to appear in this constant force mechanism is 166.7 pound-force inches. And that's just from the units, but because this is a torsional spring, we know that there has to be, that's a per radians measure. So that's how many pounds force it takes to deflect that torsional spring 1 radian. Okay. Now, what do we know about that? And what we know about K1 goes back to Chapter 5 with our pseudorigid body models. And what we do with that really depends on what sort of pseudorigid body model we have. Is this a cantilever beam? Is it a small length flexural pivot? Is it a curved beam? What do we have going on here? The problem doesn't say, so just for grins, I'm going to take this to be a small length flexural pivot. So now I would get different designs if I went with a different pseudorigid body model. So in that case, I know that K1 equals EI over L. Okay. And so as soon as an E pops up, that means I have to make a decision about what material this thing is made of. And there are a couple different possibilities. Why don't we start off with assuming that it's polypropylene, and we say E poly is equal to 0.2, what do we have? 0.2 MPSI is the units on the Young's modulus for polypropylene. Okay, and so that's 0.2 times 10 to the 6 PSI. Okay, and so what I can find then is I can find I over L equals K1 over E. And since that's 166.7 pound-force inches divided by 0.2 times 10 to the 6 pounds force per inch squared, I find that I over L is equal to a very small number. It's equal to 0.8335 times 10 to the minus 3 inches cubed. Okay, and so it's got units of inches cubed, and that makes sense since I has units of length to the 4th divided by length. And so once again, I have to make some decisions about what this thing is going to look like. If it's a rectangular cross section, then I equals 1/12 BH cubed. Okay, and so I have L and BH cubed. I've got 3 values there that there's not a lot of constraints on how those relate to each other. And so just to get a feel for what this might look like, I'm going to make an assumption that B equals H and that L equals 3H. Okay, and that's just pulling numbers just pretty much out of my head just to make this thing solvable and to give me a ballpark figure of what this thing might look like, or what a value, what sort of, out of polypropylene, what sort of beam gives me an I value of 0.8335 times 10 to the minus 3rd inches cubed. So what that's going to give me when I plug in those values, I'm going to get I over L is equal to, let's see here, I have BH cubed over 12 L, and then I plug in these assumptions and I get H to the 4th over 12 times 3H, and so that'll give me H cubed over 36. Okay. Now once again, that's just making some simplifying assumptions so I can figure out what's going on. I can then set that equal to 0.8335 times 10 to the minus third, and I can solve for h. When I do that, I get h equals 0.31 inches. Okay, and that seems like a plausible thickness for a beam. It's a square beam because B equals H, and it's a short length flexural pivot, so the length of that short length flexural pivot is 0.93 inches, which, you know, that's a fairly small fraction of my 7 inches for R2. So, you know, half of its R2 only gets half of that, but that seems like a reasonable sort of thing. So what this is going to look like is I'm going to have a small length flexural pivot here that's 0.93 inches long, and then I will have a beam with a pin and a slider on it, something like this. Now, the pin goes here in the middle of this, so this is going to give me, say, 0.465 of that is going to belong to link 2, and 0.465 is going to belong to link 1. And so what that's going to give me is, I know R2 has got to be 7.957 inches. Then I take that 0.465, and the rigid portion of this link then is going to be 7.492 inches. And of course, the R3 value is just this one, and that is 7.043 inches. Okay, and so this will give me a compliant mechanism that will do what it specified, and it will have got the cross-section properties. B and H are 0.31 inches. Now, if I was going to be careful about this, I know this has the right kinematics, but the question is, can it actually get that kind of deflection? And that would just be, I would have to see at 6 inches how much bending I'd have in this beam, figure out what the stress is, and then I'd have to go through a stress analysis and probably a fatigue analysis to figure out whether that's acceptable. If it is not, then I can keep the same I value and make the stress lower by going with a smaller H value and a wider beam. And I could iterate on that until I got something that I was satisfied with.